Hello, my name is David Gardner, and this is my lab report for Lab 6, which is based around Faraday's Law. The purpose of this lab is to study magnetic induction by analyzing the observational data of a bar magnet falling through an aluminum pipe and comparing it with a computational model. The computational model I made in GlowScript, and for this experiment, the system will be the bar magnet and the aluminum pipe, while the surroundings will be everything else. And our results, just as a little preview, were quite similar. For this experiment, we need to know three fundamental concepts, the first of which being Faraday's Law, which states that a changing magnetic field through a loop induces a changing current that's proportional to the change of magnetic flux over time, represented by this d psi over dt. The Biot-Savart law, which states that a current carrying object creates a magnetic field around it, which strength depends on the distance from the observation point and the current, represented by this I dl cross r over r squared. And Newton's law, which states that the net force is equal to the change in momentum over time, which is F net over the change in momentum over time, and the third law, which states that for every force there's an equal and opposite, represented by this F1, F2. For our procedure, our lab group placed a bar magnet inside an aluminum tube, and we measured the time it took for it to fall out the pipe from the bottom. And the reason we did this is because we wanted to see how long it took for the bar magnet to fall through the length of the pipe, so that way we can observe the impact of the magnetic force opposing gravity. And so in order to do this, we need to make some assumptions. Specifically that air resistance is negligible in this case. We also have to assume that the bar magnet acts like a perfect magnetic dipole, and that the only forces on the system are the magnetic and gravitational forces. So there are no external forces acting on, or no other forces within the system that are acting on this pipe and this bar magnet. So for our data, we ran the trial 5 times, and we found to have an average time of 1.272 seconds. We also have listed our tube and magnet properties, and our magnet weighed 25 grams and had a dipole strength of 4.613, which we found in the previous lab. And our tube had a length of about half a meter, 0.45 to be exact, and an inner radius of about 27 centimeters, or 2.7 centimeters. So first in our model, we had to create the initial conditions and variables that we would later use in the rest of our calculations. And so these include the physical constants, which has our resistivity of aluminum. We also have the geometry of our tube, which are basically the same values that we found in our experimental data for our tube, and the properties of our magnet, which is the same mass that we recorded, but also to the dipole moment that we found in lab 4. And we can use these to visualize the bar magnet in our model. So next we have to create the forces that are in our model, and to do this we have to first calculate the magnetic field from our bar magnet, which uses the dipole formula. Next we have to create the infinitesimally small amount of magnetic flux on an infinitesimally small ring. And from there, for every ring subsection, we can calculate that flux and get the current for that subsection. And then we can get the magnetic force on that ring using the magnetic force equation, I dl cross B. And we're using this B ring as our force that we're crossing against, like the second term in that magnetic force. And then knowing the equal but opposite relationship, we can add that to the total magnetic force on the magnet, since we're taking the absolute value of this. And we can create a vector from that, which we then add to the gravitational force, which is pointing in the opposite direction. And from there, we can update the velocity and the position of the bar magnet from those calculations. Next up, we have the visualization of our model. And so, as you can see here, we have a graph of our velocity versus our time. And initially, we have a very steep negative velocity, but eventually it flattens out. And the reason why this flattens out is because initially we have the force of gravity acting on the magnet, but then while we're in the tube, the force of gravity and the force of magnetism cancel each other out until the end where the magnet begins to leave the tube, and that's when gravity takes over again. And you can see our time was quite similar to our results, and from this snapshot, we can see the current on the tube induced by the magnet moving, and the red can kind of represent the counterclockwise rotation of current, and the blue can represent the clockwise rotation of current, since the magnet is moving away from that portion of the tube. Although our results were quite similar, we still had to account for sources of error, some of which may include the measurements that we used. Our stopwatch wasn't completely accurate to the time we put in the magnet and the time the magnet exited due to human error. There also could have been friction, since if the magnet hit the sides of the tube, that would create a friction force that would also oppose it. And we also have to account for air resistance, as air resistance can slow down the speed of the magnet falling through. So next up, for some hypotheticals, if the resistivity of the conductor were reduced as close as possible to 0, from Ohm's law, the resistance would eventually become negative, meaning that the magnet would slow down, or it would fall more slowly because the opposing force would be stronger due to the current in the pipe also being stronger. Um, and if there were holes or slots cut into the tube, it would affect our model since there would be less current material per cross section of the tube, which would weaken the opposing magnetic field and therefore increase the speed of the fall. And that basically concludes this lab. And so yeah.